So this is the video of describing how to make a Neopixel driver that doesn't require any code or microcontroller or programming or anything like that. This is how I made mine. This is going to be a little bit long, so I'm going to try to make this, I'm trying to break this into several parts. But the first part, in order to understand how to make a Neopixel driver with hardware only, is to describe a little bit about how Neopixels work. So Neopixels are, the other name for them is WS2812. There's a previous version of WS2811, but they work basically the same. And the way they work is basically there's a string of Neopixels, and they have three inputs: a VCC, a ground, and a data input. That's the central pin, and they're all interconnected. If you look at them carefully, they're all sort of interconnected. Each one of these Neopixels has a little chip inside. It's a programmable chip, basically, that you feed in a 24-bit value. So 8 bits for green, 8 bits for red, 8 bits for blue. And so this is in binary. 8-bit value in binary corresponds to a value of 0 to 255. And this is basically how much color, how much of each color you want in each Neopixel. So, for instance, if you want a value of, if you want this Neopixel to be completely blue, you basically give it a value of 0 for green, 0 for red, and 255 if you want the brightest level of blue. And 255 in binary is just basically 8 ones in a row. If you want it all green, you do 255, 0 and then 0. And if you want it all red, 0, 255, and 0. So basically, that's how it works. So if you feed it a value, you basically have to feed it a binary value. And so if you feed it a 24-bit binary value, let's say if it's 24 bits long and you have 8 bits for green, 8 bits for red, 8 bits for blue, you're going to have a 24-bit string just for the first one. If you continue feeding it values, the first Neopixel is going to take out whatever values it wants, and then the next values in the serial string will be for the second Neopixel: green, red, blue, and so on and so forth until the last Neopixel. You get a 24-bit value of green, red, and blue, and so Neopixel 1, we'll call it Neopixel 0, Neopixel 1, and then Neopixel N for your last one. And so basically, you have to feed all of these values in totally, and it's basically a string of ones and zeros for whatever you want each Neopixel to be. So basically, and this has to be fed in serially. Serial input. In order to get all the Neopixels to get all their values. The way the timing of the Neopixels works is you don't just feed it ones and zeros. You have to feed it ones and zeros based on a specific timing pattern, which can be a pain in the butt. The way it works is, and if you have to look at the data sheet for it, but if you look at the time signal here, to send the NeoPixel, the precise total duration per bit sent to the NeoPixels has to be a total of 1.25 microseconds. And to send, and this, is there's a tolerance of plus or minus 150 or 100, 200 microseconds in it, but for the most part, this is the value given on the data sheet. So I have tried as best as I could to approximate that value. So the total period per bit is 1.25 microseconds. So this, to send a 0, you don't just leave this at a low value for the entire 1.25 microseconds. What you have to do is you have to send it a signal of about 0.4 microseconds, and the rest of it should be about 0.85 microseconds at low. That's to send a 0. To send a 1, you basically have to send a high signal for approximately 0.85 microseconds, and the pulse has to go low for about 0.4 microseconds. That is how you send the zeros and ones to the Neopixels. And so this timing, it's plus or minus 150 nanoseconds for each of these, but this timing is so precise that it's a little bit painful to use these. It's not just zeros and ones that you're sending. You're sending, to send a 0, you have to have this pulse high for for a certain amount, for a short amount of time, and then low for the rest of the time. And then you reset the signal. So based on what your NeoPixel, how the length of your NeoPixel strip, you have to send to get the entire NeoPixel strip to light up to whatever values you want. Let's say we have n Neopixels. So the total number of bits that you have to send is 24 times n. My Neopixel strip has 144 Neopixels in it, and times 24, I had to send a total of 3,456 bits of values to the Neopixels to get the entire get a value into every single Neopixel in my strip. Okay, so which means that whatever values I want in there, I have to convert a 0 to that and a 1 to that. So on a microcontroller, you get a library for the Neopixels, and that library, generates the pulses with this exact length and this exact for zeros and ones, and you just tell it, and you just tell it where and when to, or how many Neopixels it needs. Now, there's one other thing with the timing on the Neopixels that is kind of important, and it's after you send all of these values to the Neopixels, you then have to get the Neopixels to latch those values. And so after this entire data stream is sent, then you have to send a low pulse. And that low pulse has to be, well, according to the data sheet, has to be at least 50, the latch low pulse has to be at least 50 microseconds long of a low pulse. Now, in various experiments that I've done with this, 50 microseconds is not long enough, and the correct pulse that you need to send is at least greater than or equal to 250 microseconds. At 250 microseconds, the low pulse has been low long enough, and what happens is every Neopixel value that you just sent gets latched into those chips, and the Neopixels will then light up based on whatever values you sent. So, how do we do that in hardware without a microcontroller? Because with a microcontroller, with the coding, this is fairly easy to do. You just you just turn off your output have a 250 microsecond delay, and then you turn it, and then you start sending new Neopixel values. And so that requires a little bit of thought to try to get it to work. But let's make a block diagram to figure this out, right? So you need some kind of a master clock. And that master clock is going to have to be at 800 kilohertz. So that 800 kilohertz master clock, if you take 800 kilohertz signal, it needs to be the period of each signal sent from the master clock is 1.25 microseconds. So that is how fast you need the master clock to be. And so the master clock will send a signal to the Neopixels. If you just take the 800 kilohertz master clock and you have it connected directly to the data in of the Neopixels, every Neopixel will light up or not based on the length of the pulse that's sent. So let's say you have a 67% duty cycle. Means 2/3 on, 1/3 off. At this rate, it will give you a wave that looks like this. And this will be on for about 0.8 microseconds, and this will be on for about 0.45, off for 0.45 microseconds, which, if you go back to the timing diagram here, will send a 1 to the Neopixels. So we need to find a way to have one master clock control all of the Neopixels. And so the way I did it is I had the clock sending a signal to a D flip-flop. So I have the master clock going in to the clock of a D flip-flop. And what D flip-flop did I use? I used what the D flip-flop will do is the D flip-flop will time in or clock in whatever input values you have. The way a D flip-flop works is you have a clock input and you have a data input. The data input of the flip-flop is the data that you want to send to the Neopixels. And the clock clocks those values into the D flip-flop and synchronizes everything. So the data input is whatever you want to send, whether it's coming from an audio modulated signal or another 555 or a 555 timer or some other oscillator, or this is the value that you want to send in, and the D flip flop activates with a rising with the rising edge of a clock. The output of the D flip flop is going to be Q and negative Q. So if you send the if you send the 1 in with the data in, and you get a rising edge of a clock pulse, this value is going to be 1. If you send the 0 in, if the data in is a 0, the D flip-flop will, and you get a rising edge of the clock, the Q is going to be a 0, and so on and so forth. This is how you allow synchronization of the signals. From the master clock, you need to be able to generate a high pulse and a low pulse. The high pulse is going to be the number 1 value from that we talked about with the Neopixels. So to generate a high pulse, you need some way of generating a 0.85 or so microsecond pulse every time the clock every time the clock activates. So you need some form of monostable pulse that is 0.8, about 0.85 microseconds long. And at the same time, the master clock is going to trigger a low pulse to be generated. It's also a monostable pulse, and it needs to be about 0.4, 0.45 microseconds long. Okay? Now, based on the data input that's coming through here, what we need is, this is going to be the output. This Q is going to tell us what we need, what we want to send to the Neopixels. So what do we send to the Neopixels? We need to send what our data is. But we know we want either a 1 or a 0 here, and we're going to get a 1 or a 0 here. But how do we get that 1 or 0 to translate to a 1, a high pulse, or a low pulse? And so the way to do that, because this flip-flop is either just going to be a 1, a high pulse, or a low pulse. And it's going to be high as long as the clock is high, and until the next clock cycle or whatever data bit comes in, and into the data input. So what we need to do is find a way to make the clock input as long as possible. So we want the master clock to be a very high duty cycle. You want the clock value to look kind of like this. And then you could do stuff with it. So if this is what the clock value looks like, when all we have to do is take whatever monostable pulse comes in and we just AND it with the clock signal itself. And so I'm going to draw that out right here. So if we have a clock pulse that looks like this, let's say we want to send a string of ones, high signals, to the Neopixels. What we do is we take that clock and we AND it with a bunch of high signals. I'm going to attempt to draw this out as well as I can here, where the duty cycle of the monostable pulse here is about 0.85 seconds. And when you AND the clock signal with this together, the result is a high pulse, because when this goes low, this part will go low. And so the result will be the high pulse. It'll be this in the result, high pulse string with a 850 or 0.85 microseconds or 850 nanosecond high time. Now, when you AND it with the low pulse, I'm going to attempt to draw out the low pulse, same thing will happen. When you AND these two together, this part of the clock signal gets wiped out, and the low pulse is what comes out. So you need some form of an AND gate here. So now, if this is your clock input, your D flip-flop output is going to look a lot like the clock input. And what you do is, since you have basically high pulses being triggered by the master clock at the same rate at 800 kilohertz, what you need to do is you need to be able to AND this together with the output of the flip-flop. So let's continue our diagram here. So now, if the output of the flip-flop is a 1, there's an AND. This is going to AND with the monostable pulse output, and it's going to give you the high pulse. If the output of this flip-flop is a 0, what it's going to do is, well, we have to invert this here, and we turn it into a 1, and it's going to give you a low pulse. Then what we need to do is we need to take these two pulses and we OR OR them together. So basically, it's going to send either a high pulse or a low pulse. And that output is going to go, try to make this nice. That output is going to go to our Neopixels. That way, putting it all together, you have a clock that's going at the same frequency and generating monostable pulses from each of these separate monostable pulse generators. The clock is going at a relatively high duty cycle. It's triggering the D flip-flop to clock in whatever data you want to send. If you want to send a 1, the Q becomes a 1. The monostable pulse here will activate this AND gate, and that will send a high pulse. If it sends a 0 out here, this will turn into a 1, and this will be a 0. This will be turned off, and it'll send a low pulse. And then that low pulse, either the high pulse or the low pulse, depending upon the data you want in there, either a 0 or a 1, is going to be sent to the Neopixels. And so that is how to translate it into the Neopixels. And so that is basically how I designed the circuit. Now, to make it a little bit more complicated is now you have to find a way to latch all the values in after you deliver all the values. And so there needs to be some kind of a reset signal sent to the clock to get the clock to stop clocking in values after it gets to the total number of Neopixels that you have. So now, how do we do that? Well, we need to have counters. So you need the clock to now also be triggering a counter. That counter has to count to the total number of bit values that you're sending to your Neopixels. So in my case, it's going to be n Neopixels times 24. And when that counter gets to that value, counts to 24 times n. When it gets to that value, you want it to trigger a monostable low for, as we talked about before, the low pulse to latch everything has to be 250 microseconds long at least. You want an at least greater than or equal to 250 microsecond low pulse. And you want that low pulse to go back and basically reset. You also want that low pulse to, you also want that the count to reset the counter. And basically that resets everything. And then the next cycle starts of the data input. So you basically want to stop the clock and have everything pause for at least 250 microseconds. Allow all of your Neopixels to take their data and latch it. And then the cycle starts again. After this 250 microsecond pulse is complete, the clock restarts again and starts getting the data in. So that is the block diagram of the circuit design and the rationale behind it, and how to implement it. I'm gonna put into the next video. Hopefully this helps fire up some ideas in some people as to how to implement their own, but I'm gonna show you my implementation in the next video. And hopefully this is a nice review of the timing of the Neopixels and how they work, and the rationale behind the circuit design. Anyway, thank you for watching, and let me know in the comments if you need more explanation or better explanation, and I'll be happy to answer any questions. Thanks again. Have a good day.